All right, so example number 2 is where we will start our story for today, okay? And so as we said yesterday, we really want to think about this approach to the problem as a whole, not necessarily spending too much brain power worrying about, well, there are easier ways to solve this or whatnot. We're really looking to embrace the idea of a series solution, knowing that if we choose to take other level differential equations classes, that idea of a series solution will actually be really valid and really helpful. Okay. And so knowing that we're looking for a series solution, what that means is that at the end, we're going to have a situation where we have some sigma notation. We might have some coefficients and some sigma notations, and all of those together will describe our solution in a different way, okay? And for us, we are going to focus mostly, because we're looking at the procedure and not as much like the totally nitty-gritty of things, we're looking a lot of our points that we'll be interested in will be x equals 0, okay? And so let's go ahead and begin this question the same way we began yesterday's question, which is to see, is x equals 0 ordinary? Okay. And this would be an important part to check before we get started, is x equals 0 ordinary? All right. And so we can see from here that if we look at our equation, all right, if we look at our equation, we do have indeed that the leading coefficient, our a sub 2 of x, is a 1, okay? And furthermore, this minus x, like if I plug in a 0 there, it's going to go to 0, but it's not going to be undefined, right? 0 is okay, but it's when we're dividing by 0 that becomes problematic, okay? So we can say that since a sub 2 of x equals 1, and x is, and I mean this x is defined at x equals 0, we do have that x equals 0 is ordinary. Okay. And this step is really mostly important because tomorrow when we look at singular points, we really want to see the difference between an ordinary and a singular point. Okay. But what that tells us is that it would be okay to guess a solution of the following form. Y of 0, or, oh gosh, y of x equals the sum from n equals 0 to infinity. You can write the infinity on the top. I'm probably going to leave it off because I'm a little bit lazy right now. And so I want to, focus on the rest of it rather than getting that infinity up on the top. When we plug that into our power series, we get a sub n x minus x sub 0 to the n. But since the point we're looking at is 0, we can actually turn this into the sum n equals 0 to infinity of a sub n x to the n. All right. And so this simplification right here is why we're choosing x equals 0, just to make all of this as easy as possible. All right. All right, so after we establish that it is ordinary, then we can proceed. And we're going to proceed by finding y prime, finding y prime, and y double prime, and subbing into our differential equation. All right, so that is a very common flow to a problem that we've seen, right? We find our y, we guess it, we find our y prime, we find our y double prime, and we sub everything into that differential equation. Only now we are finding these with series, right? And so we have our y of x equals the sum from n equals 0 of a sub n x to the n, right? We're going to use power rule to find our y prime. That's going to change a few things, right? Instead of a sub n, we'll have n a sub n. And instead of x to the n, we'll have x to the n minus 1. So that changes. But there's one more thing that we just need to be really cognizant about, like it is at the forefront of the things we need to change, is that index below, right? It used to be n equals 0, and now it's going to be n equals 1. All right, since this is a second order differential equation, we're going to need that second derivative. And again, we're going to change that coefficient. It's now going to be n minus 1 times n a sub n. And then the new power for x is going to be x to the n minus 2 because we lose another power. And similarly, we want to be really careful. This bottom index shifts to 2 because we're taking a derivative, so that constant from the previous one is going to go away. Okay. These will, for the most part, be the same, right? For every problem that we do in our limited scope here, because we're choosing x equals 0, all three of these will be the same. Our guess, our y prime, our y double prime. All right, but I just want us to make sure we understand where these formulas come from. I think it makes it a lot more digestible. Okay. We're going to take all of these and we're going to go back and grab our differential equation, y double prime minus xy equals 0. And we're going to sub in the y double prime and we're going to sub in the y. And so that will give us the sum from n equals 2 of n minus 1 and a sub n x to the n minus 2 minus x sum from n equals 0 a sub n x to the n equals 0. Okay. So let me just pause here for a moment and highlight a few things, right? So our y double prime became this, right? We subbed that in. Our y became this because we subbed it in. However, one thing we didn't have to worry about yesterday was any coefficients, right? So in this case, that coefficient of y is x. And so we need to bring that down when we substitute in there as well. All right. Now, I know that you know this. It's just a place where students tend to make mistakes, if anything. So I just wanted to highlight that in like the, really bright pink to make sure we don't lose any of those coefficients when we sub into an equation. All right. So we checked to see if x is 0 is ordinary. We found our first, second, and original guesses, and we subbed them into our differential equation. And now, where a lot of the meat of this problem starts is we are trying to combine into a single series. Okay. And so I'm going to do the same thing as yesterday, where I'm just going to copy this right here. I'm going to bring this down over here. I'm going to get rid of this orange tornado situation. Okay. But this is what we need to make into a single series, all right? And in order to do that, we need to change a few things, right? We need to make sure that this and this, so when I say this and this, I mean the index, we want them to be the same, okay? One is 2, the other one is 0. So we need to change that. The other thing we want to change is this power, x to the n minus 2, and this power, x to the n. We want these to be x to the n. All right. We want that power to be the same. So we have to take care of a few things first. One thing that we did not have to take care of yesterday is this pink coefficient. All right. Now it turns out that I can take this coefficient and bump it to the inside. When I do that, I end up with this part is still the same for right now, minus, what does the power of x become now? Ooh, super close. The power on the outside is just x to the first power. How does that modify your answer?
Is it n plus 1?
Yeah. So we're going to take this n and we're going to add 1. And so we'll get x to the n plus 1. And that's going to be equal to 0. Okay. So we're going to start this process by taking care of one piece of the puzzle first. We're going to see how that plays out, and then we're going to change the other piece of the puzzle. Okay. So what I mean by that is let's shift the index first. All right, let's shift the index first. And so to shift this index, I did that in blue yesterday. So our index shift, I was talking about disk method in my Calc 1 class earlier, and I didn't say the S in disk. So I'm trying to be like very enunciating with my words today, so I don't record anything else that is not good to record. But when we're shifting this index, we have I equals n minus 2, right? And we want to get that 2 down to a 0. And so that also means that n equals I plus 2. And we're only going to be shifting the index of that first series. Okay. We'll leave the second one alone for right now, and then we'll kind of see what we need to do. So in shifting that index, I'm going to get the sum of n equals 0. All right. I'm going to have I plus 2 minus 1. I plus 2, a sub I plus 2, x to the I plus 2 minus 2. And then I'm going to go ahead and keep the second one the same for right now. So sum from n equals 0, a sub n, x to the n plus 1 equals 0. Okay. Now let's simplify that first one. We should get the sum starting at n equals 0 of, let's see what we get. We get n plus 1 times n plus 2, a sub n plus 2, oops, x to the n. Okay, so in that index shift, we've actually accomplished a few things. We've gotten the index to be 0, and we've gotten this power to be x to the n, or the power is n. Okay, so for that particular series, we've fixed some things. But let's take a look at that second series now. We start at 0, that looks good. A sub n, x to the, that's still an x to the n plus 1. So if at the end, all right, so I'm going to go back up to this sort of step in our previous problem from yesterday. Okay, so before we got to all the recursion stuff, one thing that was really important is that both of these series had x to the n, so that we could factor it out. The reason why we want to factor it out is so that we can say all of those coefficients equal 0, right? So that part has to be there. We have to have x to the n in both of those, all right? And so if we go back to the problem we're currently working on, I'm going to go ahead and change n plus 1 to n. How am I going to do that? I'm going to use an index shift. Okay. So here's what I mean by that. For this part, we're going to do an index shift. And in particular, we're going to shift I equals n plus 1. That means n equals I minus 1. All right, so if you remember from the homework that was due last week, I asked us to shift the index in one direction, and then I also asked us to shift the index in a different direction. And this question right here is precisely why I wanted us to practice that skill. Sometimes we only need to shift down like we did yesterday, and then everything magically works out and we're all good. But sometimes we have to move one and then we have to move the other one in a different direction to sort of get them to meet, okay? And so if we do this index shift, and I'm going to do it off to the side, I will end up with n equals 1 a sub I minus 1 x to the I minus 1 plus 1. And I'll simplify that and put that back in the context of this problem. So sum n equals 0, n plus 1, n plus 2, a sub n plus 2 x to the n minus my new shifted series, the sum from n equals 1 to a sub n minus 1 x to the n equals 0. Okay. So I've got the powers to be the same now. In fact, it's x to the n in both series, right? X to the n over here, x to the n over here. However, in making this happen, guess what I did? The index on the bottom is no longer the same. Okay, so this is actually, I feel like, sort of a life lesson, right? Like sometimes we have all these things that we're trying to make work, and we like make a change here and that fixes one problem, but then it actually accidentally makes another problem. It creates another problem, right? And so sometimes we have to go back and forth between different strategies to actually make it into the form we want. And so here's what we're going to do, okay? This is one way that we can fix the fact that the index on the bottom is not the same for both, okay? This is a pretty common strategy. But let's think back to what this represents, right? I know this is a lot of letters, but I'm starting at a sub 0, right? So a sub 0 means that I'm going to go into here, and everywhere I see an n, I'm going to put a 0. Okay. Now, a series in general, let's maybe put this over here. So a series in general of whatever your function is, you're going to start with the first term, and then you're going to have the second term, and then you're going to keep going, right? That's the definition of a series. You take all these terms in your pattern, you add them up together. It turns out that we could take, like, let's say we wanted to just take the first term out. We could also say this is equal to the first term plus the rest of the series. You see how I just did that? I took out the first term, and by taking out the first term, I was able to say I'm now going to start counting from a different point. Now that, my friends, is very helpful in this case because we can take our series, we can strip out the first term, and by taking out the first term, we now have an index that will match the other index. Okay, so let's do that. Let's go ahead. We're going to take out the first term. So that's going to be 0 plus 1, 0 plus 2, a sub 0 plus 2 x to the 0 plus the rest of the series starting at 1. Okay, so if I were to annotate this, this would be my a sub 0 situation. Actually, I'm not going to write that. I'm going to write first term. This is our first term plus all the other terms. Right? And the first term plus all the other terms still ends up with all of the terms we want. So minus of n equals 1, a sub n minus 1 x to the n equals 0. Okay. Gotta insert a new page. Okay. So let's see what we have right now. I think we can clean this up one more step, all right? So 0 plus 1 times 0 plus 2 gives me 2. This gives me a sub 2, and x to the 0 is 1. So this quote unquote first term is just 2 a sub 2 plus, let's look at these two now. They have the same index, n equals 1, n equals 1. That's good. They also have x to the n and x to the n. That's good. Everything that we need matches. So now we can take our two series and we can combine them into a single series. Okay. So if we zoom back out for a moment, right, and we think about what we've done to combine these into a single series, we can see that we've taken more steps than we took yesterday, and that's okay. Sometimes by shifting one thing, it might intermediately cause some other things to be out of whack, but then we just use some of our other tools to fix it and make it so that we have the same index on the bottom and the same power for x in both of the series. And once we have that, then we can combine them, okay? All right, so what does all of this tell us? Well, all of this tells us that we are now ready to solve our recurrence relations, okay? And let's go ahead and do that. So step 4, solve recurrence relation. Okay. Now, of all of the steps, I think that step 4 is the one where you need to show yourself the most grace. Okay, I truly mean that. Be kind to yourself. Write out as many terms as you need to find a pattern. All right. Don't shortcut this step for yourself just because someone else looks at it and they're like, oh yeah, this is just how it works. Okay. Don't do that to yourself. Write out as much as you need to make yourself comfortable, and that is entirely okay. All right. So one thing that is a little bit different about this one than the problem from yesterday is that now we sort of have these two terms, right? We have this one and we have this one. And we know that they're going to be 0. Now our recurrence relation tells us that this thing inside the brackets has to equal 0. But it also tells us that 2a sub 2 has to equal 0. And so as we set up our recurrence relation, we actually have this additional part, 2a sub 2 equals 0, which means that a sub 2 is going to equal 0. Anytime you have like one of the terms equals 0, that's actually going to help us figure out a greater pattern here. Okay, so yesterday our pattern was like, let's split things into even and odds. But I think what we're going to find today is a little bit of a different pattern. Okay, so we've taken the first part, we've done that. But let's grab this part inside the brackets. All right, so we have n plus 1, n plus 2, a sub n plus 2 minus a sub n minus 1 equals 0. And yesterday, my strategy was I want you to get a to the bigger thing, a with a subscript of a bigger thing by itself. So that means we want to isolate a sub n plus 2, right? And we can do that by adding a sub n minus 1 and then dividing by n plus 1, n plus 2. A sub n plus 2 equals a sub n minus 1 over n plus 1 times n plus 2. And we want to say this is true for n equals 0, 1, 2, etc., etc. Okay. Now, in looking at this, all right, yesterday, we had a term in our answer that was like this, -1 to the k, right? Do we anticipate that we will have a -1 to the k in our problems today?
No, probably not.
Yeah. We don't see, there's not a negative sign here, which means that we're likely not going to be alternating signs. And so we probably won't use this -1 to the k for this problem. Okay. But that's something to kind of like think about. I know there's already so much to think about in this problem, but as you're trying to find those recurrence relations, like -1 to the k, or like an even or an odd pattern, those are ones that are fairly common. Okay. But right now, yes, sorry, is there a question?
Yeah, Judy, just this might be kind of trivial, but when you said this is true for n equals 0, n equals 1, n equals 2, is that correct? Because isn't our index 1, or does that even matter at all?
Ah, that's a really good point. So let's kind of see what happens when we plug in the numbers, okay? And then we'll come back and modify this if we need to. All right, so let's go ahead, and we already know what a sub 2 is, but let's try finding maybe like, let's plug in 1 for n. Let's plug in 2 for n. Let's plug in 3 for n. And let's kind of start there. Okay, we're going to plug in 1, 2, and 3 for n. And again, I have the benefit of having looked over this problem before, so I'm going to organize the page in a certain way that I would never expect you to be able to organize right off the bat had you not seen this problem before. Okay. So if we have n equals 1, we're going to end up with a sub 3 equals a sub 1 minus 1 is 0 over 2 times 3. Okay. I'm going to try plugging in 2. A sub 4 equals a sub 1 over 3 times 4. All right, let's try plugging in 3. N equals 3. A sub 5 equals a sub 2 over 4 times 5. Okay. Now you can see that I've almost like intentionally split my page into thirds, right? So I went across and I did n equals 1, n equals 2, n equals 3. But let's maybe take a look at what happens if we plug in n equals 4, okay? So if we do a little bit of mental math here, if I plug in n equals 4, I get a sub 6 equals a sub 4 minus 1 is 3 over 4 plus 1 is 5, 4 plus 2 is 6. All right. Now again, magically, I knew how to set things up, but mostly because I had foresight into this problem, that this first one, a sub 3, depends on a sub 0. But a sub 6 depends on a sub 3. So it's very handy that these are kind of clumped together. All right. I bet that if I say n equals 5, I'm going to get a sub 7 equals a sub, let's see, 5 minus 1 is 4. Oh, good. This is going to use the one above over 5 plus 1 is 6 times 7. And let's do one more over here, n equals 6. I get a sub 8 equals a sub 5 over 6 plus 1 is 7, 6 plus 2 is 8. All right. Now, if I had written these all either straight down my page or all the way across, I bet as soon as I hit n equals 4, I would have realized we were going in sort of like a 1, 2, 3 pattern instead of a 1, 2, 1, 2 like we did yesterday. Okay. But let's kind of simplify these sort of like we did yesterday, where we can use like a previous term to help us out. Okay. And so what I mean by that is if we go to this n equals 4, I notice that it is a sub 3 over 6 times 5. And so everywhere I see a sub 3, I'm going to go ahead and put in this a sub 0 over 2 times 3. And so I'll end up with a sub 0 over, and I'm going to go ahead and call this 6 factorial because I have 6 times 5. Oh, wait, that's not 6 factorial. Sorry. And I'm going to write this as 6 times 5 times 3 times 2. Okay. Now it looks like every 3 terms that follow this pattern, I can all say they count on a sub 0. Okay. I bet we can do the same thing over here with the a sub 4. So if we substitute in, we'll get a sub 1 over 7 times 6 times 4 times 3. And let's go to this a sub 5, right? A sub 5 is really a sub 2 over 4 times 5. But one of the things that our series told us is that a sub 2 actually equals 0. what that means is that a sub 5 also equals 0, because 0 over 4 times 5 is still 0. Well, if a sub 5 is 0, a sub 8 is 0. Give me another term that's going to be 0.
Nine.
Hmm.
N times n equals 9. No.
N equals 9? Yes. So we would say, we would maybe call that a sub 11, right? A sub 11 would equal 0 for sure. And so it's like every third term here is going to be 0. All right. And so this is sort of a pattern that we've seen. And I will say this next step is definitely hard, because what we need to do now is we need to generalize this pattern. Okay. And so in generalizing this pattern, we might notice that all the ones in this first column, right? So let's maybe divide that. All of the ones in the first column, a sub 3, a sub 6, I bet it's going to be a sub 9, a sub 12, a sub 15. But for all of those, I might be able to say a sub 3 times whatever integer I put in there, right? 3 times 1 is 3. 3 times 2 is 6. 3 times 3 would be 9. 3 times 4 would be 12. But all of those are 3k, or 3 times some integer. Okay. Now, as far as characteristics that they all share, they're all going to be a fraction with a sub 0 on the top. All right, they're all going to be a fraction with a sub 0 on the top. Our task then is really to think about how we can define the numbers underneath. Okay. So I might notice, all right, and might is used sort of facetiously here, like I would not expect you to notice this on the first go, right? But like in trying to build our ability to find patterns, it's something we would like to learn how to notice. I noticed that 3 shows up in that denominator, right? So if I write 3 as 3k, what do I put for this 3? Well, I'm also going to put 3k, right? What am I going to put here instead of 2? How could I write that in terms of something with a k? Yeah, precisely, right? This 3 is 3k, so 1 less than that is 3k minus 1. Okay, well, let's make sure that pattern works for the next one we wrote. This is 3k, right? 6 is 3k, so this is going to be 3k. And this is going to be 3k minus 1. All right. And so when we write our pattern down here, we can say that we're going to sort of start with a 2 and a 3, then a 5 and a 6. But eventually we can sort of describe these as 3k minus 1 times 3k. Because this 3k will match this 3k. And the 3k minus 1 is just the one that came before it. Okay. All right, let's try the same thing with these middle ones. All right. I described a sub 3 as a sub 3k. How could I modify that to describe a sub 4?
A sub 3k plus 1.
Yes, yes, right? Because 3 plus 1 is 4. So if I want to generalize that, I would write 3k plus 1. Okay. Now, all of these share a fraction situation with a sub 1 in the numerator. Right? So I can go ahead and put that in there. Now, let's kind of figure out where the bottom comes from. Well, this is, if 4 is 3k plus 1, then this 4 will surely also be 3k plus 1. What does that mean for the 3? Well, it's 1 less than that, so we can call that 3k. All right, so we'll have a sub 3k plus 1 is equal to a sub 1 over 3k plus 1 times 3k. And we would start by saying we're going to start at 3 and then 4, and then we sort of keep going until we get to 3k and 3k plus 1. Okay. The last one, all right, I know the last one, they're all equal to 0, but if the first clump talks about a sub 3k, and the second clump talks about a sub 3k plus 1, how might we describe this last clump? Well, we have 3k is 3. Good. 3k plus 1 is 4. This one must be 3k plus 2. And all of these happen to be 0 in this case. All right. So we need to sort of create space for that. Let me ask you a question. What happens if we had a sub 3k plus 3? Which column do you think that would fit in?
We'd go back to the first column.
We would go back to the first column. What if we had a sub 3k plus 4?
Just go to the second column.
It would go to the second column, okay? So if you've ever learned about modular arithmetic, okay, if you've ever learned about modular arithmetic, this is sort of one of the applications of it where we might have like 3k plus 1, 3k plus 2, but then this is 3k plus 3, 3k plus 4, 3k plus 5, like it kind of cycles through that, but there's only 3 categories, okay? So if you're, in love with the math world, that's sort of a nice connection to make there. But now, all right, now that we've got sort of our representations for our coefficients, now we're going to go ahead and write our solution, all right? So this step 4, we spent a little bit less ink on this than we did yesterday. But again, I would encourage you to write out as many as you can or as many as you feel comfortable with, and then look at it. What are different ways you can sort it? How might that help you find a pattern, okay? And so in our step 5, we're going to write our solution. All right. And we know from earlier that we said y of x equals the sum from n equals 0, a sub n, x to the n is going to be our solution form. Okay. Now, one question I don't want to forget about, so let's actually address this before we move on. someone had said earlier, well, how come I'm choosing n equals 0, 1, 2 when my index started at 1? Well, as you can see here, we do need a sub 0, right? We do need that a sub 0 to sort of get us started. But in particular, if we plug 0 into here, it gets us started with a sub 2. So n equals 0 doesn't necessarily mean the first term. In this case, it refers to a sub 2 as our starting term. So we do actually use all of these values, 0, 1, and 2. They just appear a little bit differently in our actual writing out of the terms. Okay. But one of the things that I find really helpful, and I know this is like maybe easier because, you know, I have a tablet or whatnot. I know writing out a lot of terms can be, you know, sort of annoying. But I find it really helpful to just sort of remind myself what this power series stands for. And so in particular, if I start with n equals 0, the way it plugs in here, I get a sub 0, x to the 0, plus a sub 1, x to the 1, plus a sub 2, x to the 2. I'm going to write out a few more just for good measure. Okay, so plus a sub 3 x cubed plus a sub 4 x to the 4th plus a sub 5 x to the 5 plus, and maybe that's good. Maybe we can kind of stop there. All right. But let's start to plug in what we found above. Okay. And so we might notice that x to the 0 is 1. So this first term goes to a sub 0. Plus the second term is a sub 1 x. Plus a sub 2 is the first time I can plug in something that I found from above. And specifically, that's 0 times x squared. Plus a sub 3. Well, that was something we had a way to write it, right? A sub 0 over 2 times 3. So I'm going to write that here. A sub 0 over 2 times 3, x cubed. Plus, let's see, what did we write for a sub 4? A sub 1 over 3 times 4. So we're going to plug that in here. A sub 1 over 3 times 4, x to the 4th, plus a sub 5. Well, we said that was 0. Okay. So I'm going to write plus 0 times x to the 5th. And then every 3 terms, this pattern is going to continue, right? 1, 2, 3. 1, 2, 3. I bet the next 3 will have the same pattern, right? But when we were looking at sort of packing all of this back up, we needed to sort of group them by like terms. And those like terms are my a sub 0 and my a sub 1. And so we're going to go ahead and grab all of the terms that have a sub 0. So this one, and in general, this. And then we're going to grab our terms with the a sub 1, and in general, these ones. And I know we don't have to write these because they're all 0, but there's a third term in that pattern, right? And all of those we replace with that pattern. Okay. So let's group our like terms. We've got a sub 0. Once I factor that out, I'm going to get 1 plus x cubed over 3 times 2 plus, it's going to keep going, plus my green terms will be a sub 1. When I factor that out, I'll get x plus x to the 4th over 4 times 3 plus, and it'll keep going. And technically, I have a whole bunch that are plus 0. Okay. And so our last step is really to say all of these, right? The x to the third over blah, 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 all the terms with the a sub 0, we can replace with this idea. And all the terms that have the a sub 1, we can switch out with the green generalized version. And so that will give us, I hope we have enough space here, we'll have a sub 0. And we're going to say 1 plus the sum from k equals 1. Okay, it's not k equals 0 because I sort of took that first one out, over x. Well, this is going to be x to the third. The next one's x to the sixth, x to the ninth. So all of these x's are to the 3k. And our denominator will be this generalized form, 2 times 3 times 5 times 6, but ultimately times 3k minus 1 times 3k. So 2 times 3 times 5 times 6 times 3k times 3k minus 1. Okay. Then we do the same thing for the a sub 1. And again, we can sort of keep the x out in the front and just start our series from k equals 1. And we grab the generalized form over there, which was the x 3k plus 1 all over. And we start with 3 times 4, we skip 1 times 6 times 7 times 3k and 3k plus 1. Okay. And so let me get this page on one page for you. I think that about does it. All right, so we've solved a recurrence relation. We've written up the solution, and all the work in that recurrence relation, I think actually pays off in writing that solution, right? I would say so much of that work and maybe mental energy and ink is spent in finding the patterns in step 4, okay? All right, so how are we feeling with that second example? Any questions coming up so far?
Judy, I think I missed it, but I was wondering why the x coefficient kind of disappeared in like step 3.
Ah, good question. Okay.
I think
And
I
no
just might
worries.
have missed it.
Yeah. Okay. So where did that x coefficient go? Super, super important, right? So this pink x, I moved it inside the series.
Oh,
Okay. So you see how this was x to the n?
yeah.
And now it's x to the n plus 1. It's n plus 1 because I really, and maybe I'll write it in the pink over here, I ended up with x times x to the n on the inside of the sum, which gets me to x to the n plus 1.
All right, thank you.
Mhm. All right. Any other questions that are coming up for folks right now? All right. So I think what we'll do is get as far into example 3 as we can. We have about 25 minutes left, which in so many other math classes means you can do so many more problems, but clearly we may or may not finish example 3 right now. Okay, but my hope is that we've at least established enough for you to feel like you can be successful on this week's homework. Okay. So that being said, let's go ahead and move into example 3. Okay. And so here we have this second order differential equation. It is homogeneous because it equals 0. And we have coefficients that are non-constant, meaning they are polynomials in this case. All right. Now it's possible for these coefficients to be not polynomials, but that actually makes the question more challenging. So what we're going to see here is primarily polynomial coefficients. Okay. And so as good mathematicians, we always want to check to see if all of this is even. Oh my gosh, that's not how you spell that. Ordinary. Okay, so we want to check if it's ordinary at x equals 0. All right. And so one way we can do that is we can take a look at this leading coefficient. And in this case, our a sub 2 of x equals x squared plus 1. Now, I believe we know that there are no real numbers that can make this equal to 0, right? In other words, a sub 2 of x cannot equal 0. Since that coefficient cannot equal 0, what we have, every point is going to be ordinary. Now we could prove this to ourselves a little bit more rigorously by plugging in 0. 0 squared plus 1 is 1, which again is not 0. Okay. So what does this allow us to do? This allows us to say that y of x equals the sum from n equals 0 to infinity of a sub n x to the n is a viable guess for a solution. All right. Now we're going to go ahead and find our y prime, and y double prime, and sub into the differential equation. All right, now we know these from before, so we'll write them out a little bit more quickly than we have in the past. But I would encourage you as you're doing your homework to make sure you understand how you get from y to y prime to y double prime, okay? A lot of these techniques that we're doing tend to be a lot easier if you understand why you're doing something rather than trying to memorize that formula, okay? Right. And again, if you're a little bit lost on where these come from, you can go back to the 6.1 notes in video, and that should clarify where these come from. All right, now we can see that we're going to have a lot more to plug in here, right? So I'm going to take this, I'm going to write it again. And make sure that I plug things in very, very accurately. Okay. So I'm going to have x squared plus 1 times the sum from n equals 2 of n minus 1 and a sub n x to the n minus 2. All right, so we've only used 2 colors up until now, but looks like we're going to have to add a third one, that this becomes this minus 4x, the sum from n equals 1 and a sub n x to the n minus 1. So that should be a single prime. That is equivalent to that. Plus 6, the sum from n equals 0, a sub n x to the n equals 0. We've got this, and we've got this. Okay. So I would say that this step, just like in all the other differential equations where we're subbing things in, it's just a nice place to double check that you've subbed in everything that you need to, okay? And so here's what we're gonna do. We're gonna go ahead and rewrite this again in step 3. I'm gonna keep the purple one the way it is. I'm gonna keep the green one the way it is. But what I'm gonna do with the orange one is I'm gonna take the x squared plus 1 and I'm gonna distribute the series to the x squared. And then I'm gonna distribute the series to the 1. Okay, so in my next line, I'm gonna have 4 series. So we're gonna write a note for ourselves here that will split into 2 sums. All right, so step 3, we are going to combine into a single series. All right, so here we go. Let's be really careful about our work, okay? So I'm gonna have x squared, the sum from n equals 2 of n minus 1 a sub n x to the n minus 1 or n minus 2. That's the x squared distributed. Plus, when I distribute the 1, then I'll just have that. Okay, so these 2 that I just wrote came from the orange blob above. I'm going to go ahead and keep the other 2 pieces the same. All right. Let's aggressively color these ones in as the orange pieces. Okay. Like many things in math, sometimes things get a lot messier before they get better. This is also probably a life lesson. Sometimes things get messier before they get better, but it'll all be okay. All right. And now I'm so glad that we asked that question about like, where did that x go in the previous problem? Because guess what we're going to do? We're going to take all of these coefficients and we're going to bump them to the inside of the series. Okay, I skipped that second one because it's just a 1. There's nothing we really have to do for it, but we're going to go ahead and bump in all these coefficients. And so this first one, I'm going to still have n. I'm still going to have n minus 1. I'm still going to have a sub n, but my x is now to the power of n. All right. So because I had x squared and x to the n minus 2, when I combine them, I got x to the n. Plus, there was nothing I needed to do for the second one because that coefficient was 1, so I didn't need to bump anything in. Now, knowing that I'm going to be trying and combining these into a single series, I might already notice that my index here for these 2 is the same, but this is x to the n and this is not x to the n. So I might need to do some work with that. Okay. Let's keep bumping in our coefficients. Sigma n equals 1 and a sub n, well, I'm going to put a 4 in the front of there. So 4 n a sub n x to, what's the power of x here?
N?
Yeah, n minus 1 plus 1 is going to give us n. Good. All right, now the last one, I'm going to bump that 6 on the inside. So 6 a sub n x to the n. All right, so let's take a look at what we have so far. Okay, it looks like a lot of these numbers on the bottom, all the indices are kind of different. So that's going to have to change. But we want to be really thoughtful about this because this has an x to the n, this has an x to the n, this has an x to the n. So really the big problem is like this x to the n minus 2, okay? So let's go ahead and shift that index of that middle one, all right? Now, for the sake of time, I'm just going to copy and paste this line. So if you are handwriting along with this, I apologize. I'm totally using my privilege here to not have to write it again, all right, and just change that second line. But if we apply that index shift, all right, and maybe we leave a note for ourselves that we did an index shift. We're going to shift it by 2. All right, so that means that this bottom will now go to 0. This will be n plus 2. This will be n plus 1, a sub n plus 2, x to the n. All right. Now, I know I didn't write out the step where I put like I equals this and then n equals this. And if you're not really sure whether the numbers go up or down, I would really encourage you to keep writing that step. Okay, there's nothing wrong with continuing to write that step. But in doing this index shift, what I notice is now all of these have an x to the n. Okay, all of them have an x to the n. That means that as long as I can get my my numbers on the bottom, I could equal to each other, then I could pack these all up into a single series. Okay. So let me ask you a question. All right, we're going to look at this first one right here. Now, I know this says 2, but humor me for a little bit, okay? What if you took this expression and I asked you to plug in a 0? What would a sub 0 be?
Zero.
Okay, it's 0 because it's 0 times a bunch of stuff, right? So in other words, a sub 0 is 0. Okay, let's play that game one more time. I give you this expression. This time, I want you to plug in 1. What do you get? 0. Good, because this is 1, right? N is 1, but 1 minus 1 is 0. Okay. So we've just established that a sub 0 and a sub 1 are both 0. Now remember, a series means you're going to add up a bunch of things. So if I'm just adding 0 and 0, I'm not changing the series. And if it doesn't change the series, I can make that index whatever I want. Okay. A sub 0 equals 0, a sub 1 equals 0. So we can change this and there's no ramifications on our problem. Okay. If we are adding a number, like if it wasn't just 0, we would have to accommodate for that. But since we're only adding 0, we don't have to worry about that. Okay. The second one is going to stay the same. That one already has the x to the n, just like this one does now. And this is n equals 0, and this is n equals 0. So we're getting closer to making it ready to be packed up into a single one. All right. Well, the third series is one where that index is again problematic. So let's play that same game. This index starts at 1. So I want to see what happens. Like, what's my a sub 0? I plug in 0. A sub 0 is 0. So I can again say, I'm going to change this index because a sub 0 is 0. It doesn't change when I add up every single term in the series. And this allows me to now have that matching x to the n as well as a matching index. And then the last one, well, that one was already good to go because we had x to the n and n equals 0. All right. So the combining here took a little bit more patience, right? The combining here took a little bit more patience because we had to move some things, excuse me, and then we had to think about what a series actually means, and that if we're adding 0, well, that's going to be okay, right? It doesn't change. We can change the index on the bottom and not have it impact our actual question. But all of this allows us to now write a single series, okay? So sum from n equals 0. I'm going to open up a big bracket. I'm going to collect all of these coefficients, and I'm going to leave the x to the n all the way at the very end. All right. And now we're going to go ahead and we're going to combine some terms. And in particular, all the ones with the a sub n, I'm going to take n times n minus 1. I'm going to subtract 4n, and I'm going to add 6. Okay. So what does that give us? N squared minus n minus 4n plus 6 is a sub n plus n plus 2 times n plus 1, a sub n plus 2 is 0. We're going to do one last thing with this line right here. This n squared minus 5n plus 6 actually factors into n minus 3, n minus 2, a sub n, plus n plus 2, n plus 1, a sub n plus 2 equals 0. So we've spent significantly more ink this time combining it into a single series, all right? Some of your homework questions might require you to do this, but as we can imagine, I wouldn't ask you something this complicated on an exam because this would be the only question I would get to ask you in a 2-hour time frame, right? But understanding how things change, like how could I make this shift? How could I strip out a first term or second term? Or how could I bump them back in because they're 0 and they don't matter? That kind of conceptual piece I can ask you to explain without having to go through all the details, right? So as you're studying for these, I definitely want you to dig in on the homework and just give it that good old go. But when we're thinking about preparing for that last exam we have, and we only have one more, but when we prepare for that last exam, I wouldn't sweat too much about like, oh my gosh, I have to be able to solve something like this in 10 minutes. I would worry more about what the flow of the question is, okay? All right, so I think we have just enough time to write down what our recurrence relation is, though we will probably not have time to solve this. Okay. So in this case, our recurrence relation is this clump right here. And I want to do the same thing I've done with the other ones, which is get that a sub n plus 2 by itself. And hold on a second, I realize I dropped my x to the n. X to the n equals 0, x to the n equals 0. Okay. But if I take this inner clump and I set it equal to 0, I'll find that my a sub n plus 2 equals, well, we're going to have to subtract this to the other side and then divide by this. So we'll end up with a negative a sub n minus 3, n minus 2, all over n plus 2 times n plus 1. Okay. Now, I think that it would be actually very beneficial for you to try to finish this problem, okay? And what I mean by that is we've done all of this work already, but the solution, like finding the pattern here, I think is much easier than the rest of the work would suggest, okay? So I think it will not take that much longer to finish the question. But I think it will be a good exercise in like, how do we lay things out? Do I think I'm going to have a pattern of 1, 2, 1, 2, or like a 1, 2, 3, 1, 2, 3? What's my pattern going to look like? And how do I write out each of these expressions? Okay, so that is my challenge to you, is to finish this problem. You're welcome to check your answer with me via Discord or Canvas when you have that. And I would be happy to look over that for you. Okay, but I think this is a good chance to say we've set up a lot of stuff. How might we figure out that recurrence relation? And the hint I will give you is that it should not be too much longer. Okay. And so I think that is a great place to stop for today. So we're going to stop the recording.